So as mentioned, Sansi kindly agreed to the people substituting for Priya. And originally he was supposed to leave earlier, so I'm substituting for him. And well, I wrote something down. And what I will do is I have given it to the tutors. I will give it to the tutors who can then send it to the participants. So what I do now is just skimming through the points, and none of it is logical or rigorous and so on, but it's the kind of thing which, when I was a PhD student, many of these things which in fact everybody knows, I found very difficult. And so I'm going to just put down some of the, and you know, it depends on your thinking. Some people are very, you give them something logical and so on and fine, they catch it. But unless I see the motivation and the result and why I have to learn all this populism, it's very difficult for me. So then I found some of the, some physical pictures and things which at least I found useful and maybe. So one thing which many people have mentioned, what I will do is basically deal with Pauli principle or Pauli Prinzip in German. And the second thing which I will do, all of them apparently unconnected. Something, all of these have been mentioned and perhaps used. But all I'm doing is I'm giving an argument which in physics is called hand-waving argument, or more sophisticated heuristic argument, because physicists actually wave, this goes up, that comes down, and so on. So it is at that sort of logical or rigorous level, which is not very high. And then third thing I'll just give you, I mean, this will be perhaps done also by Chandan on some level, but just to make it easier, there is a mean field approximation. At the end of one of his talks, he put operator equal to non-operator, just a classical variable. So you can have a mean field approximation to the Ising model, and this I basically converted into a homework problem. In other words, you do these various steps and you will get the standard solution, which you can also look up, of course, to make sure you've not made any error. And I sort of wrote it out recently. So when I didn't remember a constant, I put constant and put as homework, evaluate the constant. So sneaking out of rigor. Okay, Pauli principle. I had difficulty because it came to us in so many different ways. And it took me some time to understand that actually there is not only one quantum mechanics. There are quantitatively two quantum mechanics. And we are all quantum mechanics, so to say. So n is equal to 1 quantum particles. What you have is a Hamiltonian affecting something which has some eigenvalue, and so you get EF and psi alpha. So n is equal to 1 is kind of easy. This is, of course, an eigenfunction. This is an eigenvalue. And this kind of, when I teach the students, I called it eigenlabel. Namely, the sum of all these things, it could be NLM, it depends on what the problem is. But the basic point is, this is sort of crucial in arguing what exactly the Pauli principle is. This is n is equal to 1. So initially, you sort of say, this is involving a particular R, two particles, R1, R2, fine. So there will be some Hamiltonian which depends on these two particles, and that will act on some, I'll put capital, alpha and beta. Since it's two particles, you may have more than one eigenlabel, and this is R1, R2, and then that will be equal to some E alpha beta and psi of alpha beta and R1, R2. However, you've got to realize what this fellow is. And this is two particles. But even for two particles, you would have composed of some zeroth order Hamiltonian involving R1
and something else involving R2, and then in general involving R1 comma R2. So if you solve this, you have to solve the whole problem, and you think, fine, put it on the computer. It's just a variation of n is equal to 2. And sure, there's a slight problem because in our case, n is of order 10 to the 23, but supercomputers, whatever, you can handle. However, I realized that what the textbooks were telling us, that this is the only condition for an acceptable wave function. Whereas here, it had to be this, so let me call this 1. It had to be this for an acceptable wave function, but there was an entirely separate condition which was imposed on anything involving n greater than or equal to 2. And that condition, which is due to Pauli, of course, is that there is something called the Pauli exchange operator, and we'll talk about that in a moment. And there is a condition when this acts on your wave function, and you don't know what it is, but I'll mention it in a moment. There are some strong conditions on this. So you have a basket of solutions, and huge number of solutions. In the old, for n is equal to fine, any one of them could do, and you could. Here, no. You have to throw away the vast majority of solutions and keep only a tiny fraction. What is this condition? What is this P exchange? And to kind of understand that, let's step back a bit and not consider P exchange, but consider a slightly simpler thing, which is P reflection. So there's a reflection operator, and it hits some function, let's say R, and what it does is it converts R to minus R. Now notice that this action, and of course in one dimension, this same thing would be P sub reflection acting on f of x, and that would go to f of minus x. Now in general, the f of minus x could be anything, and it could be not that much related, or shall I say unrelated, after the operation of this reflection. For example, if I had some very funny looking function which went like this and so on, and then under reflection, so this thing which I'm plotting is f, and then the thing I'm plotting is P reflection times f, it would be something like this, the mirror reflection of this. And of course, this is big when that is small and so on. So what you are asking for is, are there eigenfunctions of the reflection operator? And it's pretty obvious they are. Of course, you know the solution. But let me pretend we don't know the solution. If you take f of x and write it as half f of x plus f of minus x, and then do the same thing, then these two guys, which you can call f plus of x and f minus of x, and this is an identity. All we've done is add and subtracted f of minus x. They have a very nice relationship with the reflection operator. So when you hit them, it is not generating any old function, but when you hit with the reflection operator f plus minus 1 of x, you basically get, just flip it around, and you get plus and minus of 1 times f plus and minus of x. So in other words, what we have here is a statement of reflection parity. And these particular functions are intimately related to the operator in that they give you this particular thing. And if you ask what they look like, well, it's clear that the f plus, which would be something like that, is like that. This would be f plus, whereas the opposite would be something like this. And these have appeared several times when you want to kill the Coulomb potential or so on. There's some condition is there. And so it's not the same as reflection, but there is some conceptual connection. Okay, so go back to the main problem. And what is the symmetry or the condition or the requirement or whatever in that case. Well, there are, in fact, this is what confused me as a young person. There are two things where Pauli is involved. And the first condition is, well, let me back up a bit. So this is our basic problem. We have 0 plus H interaction, and it has many. We want to solve the whole thing, and we start with independent particles. Now, let me kill this. So if you kill this, what do you get? And I have two particles. So again, we go back to n is equal to 2. And then what you have, your total is basically something involving the quantum particle 1, which we label by R1. And then there's also quantum particle 2, which we label by R2. And we take they could be different, but we can take them for simplicity to be the same. And if the Hamiltonians are additive, then the solutions, if Hamiltonians are additive, then the solutions are multiplicative. So this could be in state alpha, this could be in state beta, and this could be alpha beta of R1, R2. Okay, so in the old condition, once it satisfies this equation, that is H times psi alpha beta R1, R2 is equal to some E alpha beta, which I wrote down a little bit earlier, psi of alpha, then that's all you need. However, this additional condition that Pauli mentioned is there. You insist on another condition, and that involves a particular type of operation, which is exchange of a particular type. So if I had this as product of this, and what are the psi and the alpha? The psi and the alpha would involve H hitting alpha of R1, and then that gives you E alpha, psi of alpha of R1. Exactly the same thing for beta, and that's R2, and that will be E beta, psi of beta, R2. Okay, what you basically say is there's something called Pauli exchange, acts on psi of beta. And here we have basically written it as a simple combination of this, but this is general, and this is a function of R1, R2. The convention will be that this fellow is in state alpha, this fellow beta. So the picture is that what you have is an exchange, and this is a complete set of eigenvectors. I mean, if you have any eigenlabels, it's all shoved in here. Angular momentum, spin, whatever is that is in there. So the exchange is following. If you have one state here and another state there, psi alpha beta, and with some origin you pick and this is R1, and then here you pick out another electron particle, and it could even have a spin. And then if it has a spin, it's like this. So this is R2. Yeah. That's what we will come to in a moment. Right now, I'm taking it to be independent, and then you come with certain consequences, and then you say there are two types of particles. You know the answer, and in some cases you're allowed, some cases you're not allowed. Okay, what is this funny-looking exchange? And okay, one is R1 goes to R2, R2 goes to R1, and also alpha goes to beta, and beta goes to alpha. So take the first one. So what you mean is one up and one down. So you say, okay, these electrons have overlap, and that come again and again. Overlap of the wave function is kind of crucial to determining the quantum mechanics. It means that this fellow can sneak in there, and that fellow can sneak in here. And they say, okay, let them do it. They are there. I could take one of them and know who is sneaking by putting a little red dot on it. And this whole thing is basically a no red dot theorem. You're not allowed to put a red dot. These quantum particles are identical in some very fundamental sense, and this is the Pauli principle. As I told you, Pauli comes in twice. And there's no red dot. If this up and down, I integrate exchange means everything. If you flip the alpha, so this goes up. The statement is, if you do that, you would get something which looks quite different. Possibly, like I said, for the parity. So you only accept those wave functions for n greater than or equal to 2, where the original wave function mod squared. What is mod squared? Is the probability density of being in that state. Then you hit it with p, that is the probability of being in that other state. And when you take, for allowed wave functions, not working? Is it okay? Yes? Okay. So for allowed wave functions, you have to have the probability is the same. So if I have P exchange hitting your psi, whatever it is, modulus squared of that has to be original exchange alpha beta modulus squared. So this is a very peculiar condition, and it does violence. I mean, so this whole basket of solutions which you have generated, you keep looking at does it satisfy Pauli exchange? Throw, and you're left with those which satisfy this. And what are they? How are they related? Well, it's kind of this funny state is related to the following. Modulus squared is, of course, you're taking complex conjugate and just multiplying. So if they are related, then at most they could differ by a phase factor. So the point is, if you have a psi alpha beta, which I'm hitting with this peculiar exchange operator, I don't quite know what it is, R1, R2, that is equal to psi alpha beta, and by our convention, this is what I told you earlier, this is associated with the alpha, this is associated with beta. So this is 1. So when I exchange them, I don't just interchange the position, I also flip. So when you say that these things are, probabilities are equal, you are saying something actually quite deep. You are saying no red paint theorem. You are saying once you specify the quantum labels, I call them eigenlabels. And if the eigenlabels are complete, that every possible quantum mechanical label you have is there, the state, you cannot know red dots. The state is, the quantum particle is occupation of that quantum state, or not occupation, or maybe occupied by. So this is the key as far as I can understand. And what people would do is, okay, let them be different, but don't be more different than a phase factor, otherwise this will not hold. If I kill the phase factor. So then the question, oh, what is this phase factor? It is something connected with exchange. So I could write phi exchange. Okay, if this is true, then I can do it twice. So I can hit this with another exchange operator. So this is now P exchange squared. Okay, if I do that, I'll pick up another phi, and this will be twice. But now look, if I'm exchanged it twice, I'm back to where I was, because I've done this, and then I wind it up, and then I wind it down again. So therefore, e to the 2 phi times I has got to be 1. But then what can phi do? There are more complicated things, other types of quantum particles, but certainly this is a possible solution. Phi is equal to 0, phi is equal to pi. But now if phi is equal to pi, then this unknown phi exchange can then be 0, can either be plus 1 or minus 1. And it's not quite the reflection parity, but it's reflection, just put a mirror, very passive, do it. Here you're active, you're putting particles around, changing, flipping, and you find this very funny result. That identity of quantum particles somehow, at least for the simple case, leads to 2 classes of this thing. And so if I hit it if I go back and ask what is that eigenfunction business which I have, it's very much like the reflection operator. I hit it with this exchange, and I've got this unknown alpha beta R1, R2, and I should put here plus and minus, and that is equal to plus and minus 1 times psi alpha beta plus and minus. This can be called many things, but we could call that, in analogy with the reflection, an exchange parity. So this is the first part of when I was trying to understand it as a student, that in some mysterious way about the identity of quantum particles, somehow underground connection with collapse of wave functions, and okay, it's connected to the coherence in a very fundamental way, and the whole is implicitly relying on the fact that the wave functions are not two widely separated delta functions. They have, so this fellow sneaking in there, therefore it's all one wave function, which is realized in fact when you do with hydrogen molecule, Heitler London. In fact, in some senses that's taking it to the extreme. One wave function, finished. Everybody occupies that. So this exchange parity, and then the other question, which is, so the exchange parity for particles. Then the question is, which is which? Which particle have exchange parity plus 1, and which have exchange parity minus 1? And there Pauli comes in again. And what he did was, he looked at field theory about interacting quantum particles, and he found that with certain general conditions, which are not restrictive, the whole thing is invariant under something called CPT. So invariant means it's sort of like an identity. What is C? It is charge conjugation. Wherever you have electric charge, you put minus electric charge. What is this? Oh, that's just my reflection fellow. So wherever I have R, I go into minus R. What is this fellow? Wherever I have time, I go into minus time. But at least was mentioned you run the clock backwards. But then when I have spinning objects or some kind of angular momentum or whatever, it kind of goes the wrong way. And therefore, if I have a sigma, this is sort of, it's all hand waving, this goes to minus sigma. So spin is somehow underground entering the whole picture. And Pauli, when he did the analysis, found that this fellow is connected with integer spins, and this fellow is connected with half integer spins. And of course, historically, integer spins have been named after Bose, so these are called bosons. And these things, half integer, are called fermidons, although strictly we should call them Fermi-Dirac particles, and that should be Bose-Einstein, actually more Bose than Einstein. But this is very nice because now we've kind of embedded this in all particles that have n greater than or equal to 2, whether they are interacting or not. So this is or not. But the same thing would apply if they are interacting, and that is the problem. Because this is a condition for n is greater than or equal to 2. So what would happen for, let us say, n is equal to 3? Well, n is equal to 3, you can just write it down. It's a little harder to do, but you can write it down. And so n is equal to 3, you would have some kind of funny condition, alpha, beta, gamma, R1, R2, R3, and this fellow will be associated. All the usual things go around. And notice, this thing should obey, it should be pairwise Pauli. That means I can interchange these two, or those two, or these. But now we have 10 to the 23. And all of them, any two pairs, if you interact, you've got to have the appropriate sign for that particular type of quantum particle. So this immediately is telling us that it's kind of difficult to do. But in any case, for this case where it is non-interacting, can we write down or can we understand the basic function? What is the function for n is equal to 2? And for the non-interacting case, and then we would just say psi alpha beta. If you just go back to what we wrote earlier, it is psi alpha R1, psi beta R2. Okay, that's just what I told earlier. This is basically the particle at R1, and this is something else, that's the particle at R2, and one of them is spin up, let's say, one of them is spin down, etc., etc. Now, if I hit this fellow with a quantum particle, I'll flip it. So let me take as a trial, when I'm flipping it, this is alpha R2 and psi beta R1, and if I put a plus and minus here, you can see that I should put a plus and minus here, and this is a candidate for an acceptable many-body wave function for n is equal to 2. And when you look at it, two things strike you. First is, wow, this is something like, I can write this as, I mean, it is the form of a determinant. So it is something like a determinant, which will give you the minus sign. Plus sign, so you have a determinant, and if you flip the signs of a determinant, for some reason that is called a permanent. Okay, so then you find I've solved the problem. No, you haven't. First of all, you've done it only for this is equal to 2, and you have a 10 to the 23 determinant, and you've not even tackled the basic problem, which is how to handle interactions. Each time you do something, on numerical, oh, wait, we have to throw away most of them. And then you say, okay, abhi ho gaya. Then I mean, it's ridiculous. You want a simpler way to do it. What is the simpler way? The simpler way is this general Pauli, which is applicable whatever the nature of the interaction. Right? You have Coulomb, you have something else, you have looking at quantum spins. It's all applicable to all of them. So therefore, create a new formalism, and the new formalism builds in the Pauli requirement from the very start, and you rewrite your Hamiltonian in terms of these new operators. And what would you call such things? The original Schrodinger's equation was called first quantization. So it's pretty obvious that the thing you should call it is second quantization. So first quantization is, where did we introduce operators? Well, we had X operator, P operator, Px, that fellow. So you had operators coming in at this level. Yeah, question. No, it's the other way around. You're defining a fermion as that. The basic definition is that you define the fermion as something which is odd, has odd exchange parity. Then Pauli comes and says, look, CPT, etc., etc. And if you have odd exchange parity, it is half integer. So the starting point is the exchange parity, and then you find it is spin.
Okay.
So that's when I was a student, I got totally confused. Because I didn't realize there are two Paulis, not one. And first he says demand exchange parity eigenfunctions as well as being energy eigenfunctions, simultaneous diagonal, you know what I'm saying. And secondly, there is a connection with spin. In fact, therefore, if I have something like what I wrote down here with a minus sign, you can immediately recognize that what happens if I insist on taking such a particle which has odd exchange parity and insisting that I have two electrons in the same alpha. What is the amplitude or probability that this happens?
0.
So it's not something that you put by hand, oh, spin half and so on, the wave function be 0. It's the other way around. It comes as a consequence of all this. Okay, so now I will try to handle the next problem. So is this okay? Any questions? And remember, all of this is essentially non-interacting. At least the examples which we had are non-interacting, although the requirement of being Pauli symmetric plus and minus is whether it is interacting or not. And therefore, when you deal with interactions, build it in from the very beginning. And how do you build it in? I will then give a literally unbelievable argument. Namely, it is completely hand-waving and It's just pictures. Okay, so the same thing I will do. Way to approach to second quantization. Okay, start with a notational joke. This is, how would you call that? You would call it a bracket. Okay. How would you call this? You would call it a bracket. And you could put a C in the middle if you want. So this is Paul Adrian Maurice Dirac, and British, Swiss, sort of a little confused. And so he wrote this beautiful book in the start of quantum mechanics, and introduced this very compact and elegant notation, which people are using and were used in the series of lectures, and which I will also use in hand-waving introduction to second quantization. There are many other ways of approaching, but this is one way. I should mention Dirac because he was a big friend of Abdus Salam's. And when Professor Salam started the International Center for Theoretical Physics, he used to visit him from Cambridge. And he liked to walk in the park. If you have seen pictures of ICTP, someday some of you will go there. It's an incredible place. And there is a castle, usually the German, European things, the local Maharaja, local Zamindar has a castle and then a park around it. So there was a park. And Dirac used to like to walk. So he used to go up, walk in the park and come back. Now, the building, the center main building was built in such a way, there's a grassy slope, extremely steep. And then Dirac used to come running down, and very tall, gangly fellow used to come in. Then somebody went to Professor Salam and says, you know, गिर जाएगा तो कुछ हो जाएगा तो बदनाम होगा, नया institute है, कुछ करो. Then they built a staircase coming down from the thing, and what is it called? It's called Dirac Scala. Scala means staircase in Italian, and so that's just a side story. Incidentally, do go to this site. They have 40 conferences a year, and according to Professor Salam's vision, developing countries will be helped. So if developed country people come, maybe they pay, but nothing from developing country people. And we are technically a developing country, and we still are, still a majority poverty country. So if you see a conference which is of interest, could be in magnetism, could be in anything, apply. Doesn't hurt. And if you get selected, they give you fare, they give you per diem, they give you a nice house, you have pizza, you have all kinds of good things to eat, and you get really first-class people who are running it. So I was there for quite a while and ran some conferences myself. Okay, so I'll give you this hand-waving argument for second quantization involving bras and kets. And basically, what we do is the following. We have learned from the previous that there is not one kind of quantum particle, there are two kinds of quantum particles. So if you are having something, what do you want? So first thing you need is an empty dabba, which is a vacuum. And you put particles in the dabba. And then they interact, you put two, fine, they will interact, they'll do all kinds of things. So you need a way to describe adding of particles to the empty dabba. So if there's something in the dabba and you pull it out, in fact you want to count how many are there, na? So 45 are there, you nikal, acha ek hai, do, gin ke karte hain, na? You have a vacuum state, which is a particular case, and you want to add particles to it. So there are two particles, so let me do this. Let's call this fermions, and let's call this bosons. You need operate, dabba doesn't care. You can have fermions and bosons. You can have bosons interacting with bosons, fermions, you can even have fermions interacting with bosons. Right? Electron-phonon interaction, what is that? So this fellow refers to things like electrons, like protons. You can have neutron stars, have degeneracy and so on. And this fellow refers to things like phonons, photons, things like helium-4, which have superfluidity. So this has the power to deal with anything. And that's what the situation is. So I can have this, and I hit it with this state. I generate a new state. What will I call it? Obviously, I will call it with the quantum number put into it. What do I have here? So what is the thing I want to do here? I have various types. So I have C dagger, I have C dagger C, I have C alpha, and this I can call N alpha, the number operator. I destroy what is there, look at it, and put it back. So this is a creation, this is a preserving, and this is a destruction. So in some general way, Brahma, Vishnu, Maheshwara. Yeah. So this is kind of interesting, but that's for that type of particle. What about this fellow? Oh, same thing, no? I will have A alpha. Quantum numbers could be different, of course. And then again, I will have operator involving both. And again, I will have it. So what we will do is we will derive relationships these have to obey. And let me begin by defining something called a commutator, which is AB, and that is nothing more than AB minus BA. And then the opposite of that is, of course, an anti-commutator, and that is traditionally, I think it may have been due to Dirac himself, that is defined as AB plus BA. So you see the A minus sneaking in various ways to distinguish how these fellows behave. Okay, so now I have created a state. Oh, then I have this other fellow now. What happens? This is when this fellow hits a vacuum. You have a particle. Dabba is now filled with one particle. What happens when this fellow hits it? It destroys whatever is there. So what you have is nothing. So property is it destroys the vacuum. So I mean, it's given in the notes, so I won't keep. I'll do it. There's a whole series of things which you can calculate, and of course, this is with one of them. So this is clear. What happens if I add 2? Oh, then we'll call it alpha beta. What happens if I do a Pauli exchange on alpha beta? Then I will get beta alpha. What happens if I do an exchange on beta alpha? And that would be written as this notation is this. But now this fellow is related to that because it's an odd Pauli parity quantity. So this fellow is minus that. So after fiddling around a little bit, immediately get that C alpha comma C beta anti-commutator is equal to 0. Now what is this dagger? It's a Hermitian conjugate. So whatever I have here, I can take Hermitian conjugate of both sides, and then I will immediately get that the destruction operators also anti-commutator. Can I do it for this? Yes. In fact, that is your exercises. What I'm sending you, each step on the left-hand side, you can translate here and get this. You still have one more, and what is that? Well, let me erase this and then do that one thing and then stop. So what you have there is this number operator alpha hitting alpha. Physically, it is, what is this? This you already know, no? This C alpha dagger. You know what this is. It is C alpha dagger, C alpha. In fact, if I put in something else, not alpha but gamma, which is not equal to alpha, this will give me 0. Why? This will be C dagger gamma, C gamma. It will move through this with a minus sign. It will then hit the vacuum. And when a destruction operator hits the vacuum, it gives you 0. So I would get 0 if gamma is not equal to alpha. If gamma is equal to alpha, so I have alpha here, then this is what I would like. that it counts, right? Destroy it, count it, put it back, get back the same state. So then you can then work out what kind of thing you want in the end. It's given in the notes. You have this anti-commutator. You need the one. This is the same one. Okay, so now I have an algebra of operators, and notice this crucial point. I have built into my algebra the Pauli exchange symmetry. So now, what do? Well, I had Hamiltonian. Then you say, fine, can I write the Hamiltonian which I had earlier in terms of these operators? And that would be tremendous, because that means whatever manipulation you do or perturbation you do, many-body perturbation, it will begin and end with some combination of these operators. And their algebra guarantees that the condition is satisfied. Okay, so let me sort of do a little more and then end here. And I'll just state, so our basic story is now that the Hamiltonians can be written in terms of these operators. I can have a Hamiltonian for fermion operators, and the Hamiltonian, see, this was a kind of a number operator, na? So I can then, in some form, deal with number densities, right? So I have operators for number densities. In fact, I can then insert a sigma, and I can deal with spin densities. And I can have a Coulomb potential. What is that? Some density times 1 over r, another density, density meaning charge density. For the case of spins, I would have a spin density and then a j, r minus r prime, and then a spin density. So then all of your Hamiltonian and the perturbation and other things are stated in terms of these operators, and then I can do perturbation theory, I can do all kinds of things. So let me just write down a picture. You will sometimes see this, that a potential is like this, and I basically have some rho of r, v of r minus r prime, rho of r prime. You could put a dagger, but it doesn't matter. And this could be anything. It could be Coulomb, it could be any kind of, it could even be delta function. And then if I write rho in fact is psi dagger psi, because that's the operator, and each of the psi's in terms of the operator, in terms of the C. And so in the end, you will typically get that this thing is something like over wave vector space. It would be some V of Q, and then what I would have here is some operator in Fourier space, which is rho Q, and then rho Q. So what I'm saying, and the other case would be something like a J, so you'd get a JQ, and then some kind of spin operator. So I'd have spin-spin exchange and so on. If I set this was mentioned earlier, the spin operators just to be sigma z, then that basically goes back, all this stuff goes back to classical. And as was mentioned, your interaction between the quantum spins on some limit reduces to an interaction between classical spins, and the classic thing which people have written down is basically Sj, sigma I, sigma j. So I'll stop in a minute or so, but then the question is how to solve such situations. And I found a good way to teach it is to add another term, and you say, okay, let the sigma I interact with some B0, which is an external magnetic field. And the reason for that is, and that's given in the homework, first step it is killed J. What is the sigma? Plus and minus 1. It's just like sigma z having eigenvalues plus and minus 1. And if I kill this, I have a completely soluble model. And what I get is the average magnetization, well, average sigma, I should say. The magnetization is an average of the sigmas, and that will be related to the B0. You can solve that exactly and get how it behaves. Then the essential physics behind the phase transition is, this is an external field, which is you can turn it on, turn it off, whatever, and you can leave it on. And what these, and that is just a single sigma, na? The problem is you are multiplying sigmas. So you have these spins and they're all going up, down, up, down, up, down. And the notion of a phase transition is that the percentage of up and the percentage of down are always cancelling, except when your temperature falls below a critical temperature, what you had earlier, which is Tc, and you had 50% up and 50% down, all the way, 50% up. At this point, something happens, and you get 51% up and 49% down, and then it continues, and what you have is a situation like this. There is a Tc, and your magnetization, which is nothing more than the average sigma, goes like this, and so I can have this and then another possibility, and it goes this way, and the spins can all align. This is what I meant by, so now 50%, 51% up, which is up, is dominating. I could also have the other, where 49% are up and 51% are down. So that will be a second branch, and then these other fellows would then. So this point is the critical point, and that is where you have symmetry breaking, which was mentioned. And what do you mean by symmetry breaking? Well, you go back to the Hamiltonian, which I wrote here. If I flip the sign, nothing happens. So the Hamiltonian does not care. I mean, you can flip every single spin, the energy should be the same. And this is a very peculiar situation that the ground state doesn't have the full symmetry of the Hamiltonian. And you may say, oh, hydrogen atom, I know that, because hydrogen atom is rotationally invariant. S state is rotationally invariant. Once I go to higher, I mean, you have angularly varying states. But those are excited states. And here what you have is the possibility of choosing one of the two possible symmetries in a macroscopic sense. And so that is the symmetry breaking which people refer to. So I'll stop here. And if you go through that section, what I have done is I've introduced, well, basically, let me say what I introduced, namely a clever way of handling, I guess it goes back to Weiss, this thing which you don't know how to handle. And this is fluctuating, that is fluctuating. But as I said, it's below some Tc, it's 51% up, so the average is non-zero. So what you deal with it, it's an approximation, that you have sigma I seeing the average of that neighbor, which is independent of site, so it's every actual thing, which is equal to m. And then the other fellow, the exact opposite. Sigma j sees the average of this, and that is, of course, also m. You think that's it? No, because if I take average of both sides, the left-hand side doesn't agree with the second, so I have to subtract off a basic average sigma squared, and then it sort of works. And that turns out to be important for the free energy and so on. So notice what is happening. This fellow is just a constant. In fact, we put it as magnetization. So this is also a constant, which is magnetization. Oh, but now you're back to an external field interacting with the spins. I wrote it as B0, except external. Now this is B internal. So that's the rest of the problem set, evaluating the mean field solutions. In fact, you can even get mean field version exponents, which happen here because this second order phase transition. Okay, that's basically all I wanted to say, and notes will come to you in some form or the other, and I hope you find them useful. Thank you. Yeah, so now I think what we can do is general things being discussed, and both Chandan and Mustansir could talk. I think we still have time on anything interesting. Or spin glass, did you mention the spin glass solution or Parisi? Talk about Pauli.
There's so many stories about Pauli that one should mention one or two. Pauli was a character, I'm told, before my time, but he was a very exacting and slightly scathing person. So he had, he had very high standards. And, one of the famous statements he made about somebody. So somebody, had done some work, and people couldn't understand whether it's correct or something, and so they asked him, "Look, Pauli, what do you think?" His answer was very insightful. He said, "It's not even wrong." You know what he meant? You know, right is one thing. You try to be right, but sometimes you make mistakes. You can be wrong, but it's not even wrong. Not thinking about it. So this is the way he was. I mean, he would say things like this. Okay, this was one story. There are many stories, but I somehow now can't remember. Yeah, so, I mean, Pauli was a theorist. And when he would go and visit labs, people would happily show him the equipment, and after that it would stop working. All the equipment would go bad. So, is this correct? And then one day, So, one day, yeah, right. He had all these powers. Yeah. Okay. Then, I'm told that when the idea of spin first came around with Uhlenbeck and Gauss-Schmidt, Pauli just said, "This is rubbish. Don't even think about how can you have things like spin? I mean, forget it. I mean." And then, without telling anybody, he began to work on spin. And invented Pauli's spin matrices and so on. Then what else? So, have you heard of the name of C.N. Yang, Y-A-N-G, Yang? Very well-known physicist. He is the person who, along with T.D. Lee, pointed out that parity is not a law of nature. I mean, there are phenomena that happen in nature that, you measure something and you take a reflection of that and you find it's different. So Yang was Yang. Now, when Yang was a young man, he applied for a job at Princeton. And he went to give a talk, and Pauli was in the audience. So, I mean, this Yang told us, but so he would just heckle him. I mean, you are wrong. I mean, he didn't know what to do. And he wouldn't say further why you're wrong or what's wrong. But Yang would continue. Afterwards, "Mr. Yang, you're wrong." I mean, remember, Yang is young and Pauli is Pauli. I mean, you forget about age. So 3-4 times it happens, and Yang said that he gave up. He went and sat in the audience. At which point, Oppenheimer took over. Oppenheimer, I know you all have all heard about Oppenheimer. There's a movie, right? Anyway, so Oppenheimer was the director of the Institute for Advanced Study. So he went and sort of patted Pauli and said something to him. After that, Yang came. Pauli did not interact. And Yang gave his talk, and he got the job. He also won the Nobel Prize very short. Okay. Yeah.
Just as a side point, our distinguished colleague was a PhD student, and he was at Stony Brook at a time when C.N. Yang was also there. Sorry, I'm revealing secrets. I'm talking about you. Yeah, it's kind of interesting and exciting to meet some of these legendary figures. And just as some of you are doing being tutor for the course, he was sort of a tutor in a course that C.N. Yang gave.
I was a teaching assistant for a course that Yang taught. It was a lovely course. It was a course on physics for non-physics majors. So undergraduates who were dealing with poetry and with the arts and humanities all took the course. And it was a course in the sense that he conveyed very deep ideas like parity, symmetry, this, that, without using equations. And he conveyed these quite well. They would do homeworks and then grade them.
How do you grade a sonnet? You take its square root. It's called square root of a sonnet. And Anushila, who is wandering in, science media correspondent, director of the Science Media Center at TIFRH. Yeah, what was I going to say? I've forgotten. No, I've forgotten my train of thought. I was just talking about square root of a sonnet. Yeah, she ran in fact, it's a play by some playwright in Bangalore, Nilanjan Chaudhary. And it has been put on in California, but she brought it here. And so they were tutoring our students. So these are all standard PhD students like you. They have thesis work and all that. And somehow she persuaded them to. So one was, the story is of he was a student in Cambridge, and Sir Arthur Eddington. View, and the is square root of a sonnet. And I think the last few days back they had their last presentation, in fact in Bombay, the Homi Baba. And I eventually it will be put online, so you should watch that. Yeah, in fact, Chandan knows him.
Yeah, Nilanjan actually is, he was sort of trained as a computer scientist. So he was working in Bangalore for a while, and after earning a lot of money, he decided that he has to change his profession, so to speak. So he gave up his job, and now all he does is basically writes. So he has written several plays. He has also written a novel, which is also available. The next play that he is working on is actually on Abdus Salam.
Yeah, since Salam's name came up, let me take that. So, of course, I mentioned I was at ICTP for many years, and they have a interesting program. In fact, you should watch, apply to some. Okay. So Professor Salam, I used to be an associate when I was young. I was at, I guess, University of Hyderabad then, and those days money for travel, I mean, forget about it. So, I mean, Mustan knows the situation. And they would give you some peanut amount in dollars when you go to some conference, which you would pay for taxi fare to the conference, and then your friend will bring you dollars. So that was the overall story. So I visited the ICTP and met Salam. He was amazing. He was in his 30s when he founded the institute to help developing countries. And in his 30s. And he was simultaneously doing the work for which he got the Nobel Prize eventually, along with Weinberg and Duashaw. And so I visited, and he liked South Asians, and he would interact nicely with all. So there'll be Indonesians, there'll be Zambians, there'll be some developing countries only. So he called South Asians, so Indians, Pakistanis, whatever. And then I said, so where are you from? Where are you from? And I said, Professor, I'm from University of Hyderabad. He thinks a bit, and he knows this. So that's different from Osmania, right? I mean, Osmania was more famous than Central University, maybe it still is. But people in Hyderabad didn't know the difference between Osmania and Central University, but Professor Salam did. He kept track of things. And the other thing which he told all of us, this is another visit, I think I met him 3 times. He gathered, he has in his writings, every scientist should do their science, do it well, and there is only one standard, and that is international standard. I mean, you cannot go and say, Saab, hum garib hai, hum ye nahi kar sakte. Okay, there is one standard, that's the frontier. You have to bring yourself up to that. And he said, in addition to your personal ambitions or whatever you want to do in science, everybody should have at least one developing country topic. It could be anything. It could be pollution, could be climate, could be poverty, whatever, primary education, and they should do both, which he himself did in founding this institute. Yeah, so I think we are nearing the end. Shall we close?